So I'm going to be computing total distance. So I'm going to, first of all, because this is state, this is a value that needs to be retained even on invalid cycles. So the total distance is meaningful always. And because of that, I need to go outside of the valid condition. And this logic is in stage 4 of my pipeline. So I have to make sure I'm putting this statement in the context of a pipeline stage. So I do @4 and total distance, and we'll make that one also only go up to 31 to 0. And maybe we should make that bigger. So this is going to be accumulating a lot of distances. So let's just go ahead and make that 63 down to 0. And this is going to, it's a mux, so we're going to use the ternary expression that we've learned already. And I'll go ahead and format this in the recommended style. So we have, first of all, we'll do our reset condition. And like I said, I'm going to hook up reset to the input from the module. And in TL Verilog context, you can refer to system Verilog signals using the star notation. So I'm going to use star reset, and that's going to be the reset signal that's defined in this macro, which we can see over here. So this reset. And on reset, we're going to use a value of 0, as many bits as needed, so 64 in this case. And otherwise, we have a valid case and an invalid case. So if we're valid, that's the case where we need to add the value, the CC value, to the current total distance. Or really, I should say the previous total distance. And we refer to previous, if you note here, we're taking total distance from stage 5 and using it in stage 4, right? That's how we retain the value in the flip-flop. So we take the value from the previous computation, or computed in the previous transaction in the pipeline, we can say. And we use that in this calculation. And the fact that we're consuming in stage 4 a value from stage 5 means that we need to reach one ahead in the pipeline. And that means, in other words, we're using a value from the previous transaction in the pipeline, whether it was valid or not. And so we can reach from stage 4 to stage 5 by using this ahead by 1 operator. And so this is the previous total distance. So all the same, as we discussed before in computing the Fibonacci sequence and the counter. So the previous total distance, plus the CC value. And if I'm not valid, that's just going to be the default case. So the default case is to just use the total distance. So we're retaining the total distance. And there's actually a shorthand for that, which we can use. The retain keyword is equivalent to previous value of the value we're assigning total distance, which has the effect of retaining the value. Alright, so that's going to be my expression for total distance. This addition is the addition here, and this chained ternary expression is my mux. So I'm going to go ahead and compile that. You can also compile with Control-Enter. And my new circuit diagram with total distance now. And I can look at this version of code in the navTLV. I can see some highlighting where signals are not assigned. This is, warnings. I'm not sure what this one is. This one is the warning for valid, saying valid is not assigned anywhere. And I can see those errors in the log as well. It's good to check the log always. So these are my unassigned signal warnings, which is intentional. And my verilator simulation. Everything passed, everything was good. And I got my waveform, so I can zoom in on my waveform. And again, we have the same stimulus. So my 6.6 value is becoming 24. And now I should have a total distance signal. So my first, let's see, the first computation that is not reset. Give a little more room here. So 29. Where is that coming from? So I guess a few. Okay. So I guess the first computation that was not reset was this F. So that's my first count value, and then the next computation produced A, so adding A to F I got 19, and then I got a 10, 29, and then I got my 8 over here that we were looking at before. Remember, this is hexadecimal, so 31, and so on. You know, I was having a little trouble figuring out what was going on here with the first computations. And you know, just to see some better methodology here, we can actually use a reset that is properly pipelined itself. So it's a little bit cleaner to define a reset for the pipeline, and I can hook that one up to the system Verilog sort of global reset, and then use that reset here. And this way, reset sort of marches through the pipeline, and it's, you know, this is establishing my association with the, you know, between the global reset signal and the computation that I'm performing. And if I compile this, you'll see in my diagram an error. So what's my error? Let's check the log. Indentation is too deep. Let me see what I did. Indeed it is. So let me correct that and compile again. And you'll see in the diagram that now I have a reset signal that hooks up to the pipeline in the beginning stages and marches along. And now if there's any other state associated with this computation that needs to be reset, I've got a reset, and I'm going to apply that reset to the computation consistently throughout the pipeline. Right here I only have one state, it didn't really matter. But if there's other state in the pipeline, it's all going to sort of reflect that reset naturally at the same corresponding time. So that the transaction, you know, you'll have transactions in the pipeline that are during reset, and you'll have transactions in the pipeline that are after reset. Using this reset throughout the pipeline consistently, you'll get consistent application of that reset where a given transaction will be reset or not. Okay, so now I'm going to jump back to the slides, and you guys will do a little exercise on the calculator logic that you're working with. Okay.